My name is Felipe. I'm like a senior machine learning research scientist at Layer 6 AI. And this is we're a company that basically focuses on doing research competitions like Kaggle competitions. And we also do use cases. Most of the use cases have to do with TD, that is our parent company. And this, I would like to talk about our latest paper that we published in ICML just a couple months ago. And this will be a little technical, so we'll see how it goes. I found it quite interesting. This was in collaboration with the Vector Institute. Particularly, you may recognize some of the names in there, Gary Huang is my co-author, and Maxine is our CTO, and Jimmy Ba, if you don't know him, he was the creator of the Add-on Optimizer or the layer norms. So he's a prof at Vector Institute and U of T. So, all right, let's start. So I wanted to talk about the transformer architecture. We're really interested in understanding the transformer architecture and what were the problems that it has. Particularly, there was something that we didn't understand about the transformer, and that has to do with the warm-up phase. I will talk about that in a second. So we investigated what happened with it, and our investigation led to some remarkable results and understanding of what happens when you change the way that you initialize a model from the global perspective instead of the local perspective. I'll talk about the results at the end. So the transformer architecture is an encoder-decoder architecture that is extremely powerful. It takes, the encoder by itself is a sequence, is a residual architecture with changing between attention blocks, multi-attention blocks, multi-headed attention blocks, and multi-layer perceptrons. Meanwhile, the decoder architecture has three kinds of layers. It has the self-attention, it has the encoder attention, and then it has these feed-forward blocks. You repeat that both in the encoder and the decoder a certain number of times, in this case, n times, and you obtain the transformer architecture. I want you to notice certain things that are important about this model. The first one is that you have the residual connection. That is really important, and that is designed in order to backpropagate signal to every single one of the blocks. You also have the multi-headed attention. That is one of these amazing things that have been discovered in the later years or created. I would like you to try to learn more about it, but particularly I found this paper recently called Hopfield Networks is All You Need, that is able to interpret the multi-head attention from a different point of view and basically tells you that the number of patterns that you learn grows exponentially with the dimension, and that will be relevant later to some extent. And the other thing that is important is that every time that you see a norm, it basically means a layer norm, and that's an object that is designed in order to control the size of the signal. Usually for the forward pass is designed to control that side, but as we will see, has a bad effect when you want to do backpropagation. So what happens with the transformer? If you want to train the transformer, suppose that you want to train it, say, for machine translation, that is what I'm going to use it for. We're going to train, say, for English to German. It is necessary for many, many data sets to have a linear warm-up phase. For your learning rate, you need to start from 0, go up, and then decrease. And this is really strange. People didn't know what was going on there. If you try to do the usual warm-up phase, that is just a flat setup for a while, a high learning rate for a while, and then the usual decay, either cosine annealing or the inverse of the square root of the number of steps, anything that you want, it doesn't work. It really needs this linear increase. And that was confusing. We didn't know why. So we also noticed that if you remove it, if you actually get rid of it, something happens with the signal at the beginning in the input embeddings. We found that if you do that in the input embeddings, the gradients are almost non-existent. There is a gradient vanishing. And why? I mean, you have these residual blocks. You have these residual connections. So you should have signal there, but the signal was just disappearing. And the only thing in the middle was the layer norm. So there was something going on, and we wanted to understand it better. And that was in fact the case. When you look at the layer norm, The layer norm in the forward pass, it does a great job, but in the backward pass, it reduces the amount of the signal inverse proportional to the forward pass, to the signal of the forward pass. So if you stack many layers, this begins to compound and basically making the signal disappear at the beginning. So then there is a problem there. We also saw that from the experimental point of view, like we train a 6-layer transformer without no warmup, and we saw that the signal indeed, as you go through the forward pass, the signal increases, and that forces the signal to decrease in the lower layers, in the back propagation. So to summarize, with our layer norm, we have a magnitude in the backbone that it begins increasing, and it increases a lot, which creates a problem. So like it's not good to have. With layer norm, we have the problem of this backpropagation. And the solution that we came up with is like, okay, let's try to remove the layer norm and control the size of the signal as it goes forward by changing the way that the parameters are initialized. I would like to mention that before I continue, that one of the major reasons that happen that this warmup phase is needed has to do with the inverse of the square root of the second moment that shows up in the Adam optimizer. That thing has been shown in a paper that is called Radam to have an unbounded variance. In most cases, in most data sets that people have encountered, this unboundedness that has no effect. This is the first kind of data sets or models where actually in something similar to autoencoders may happen as well, like bees may suffer for something like that, but we don't know for sure. But in these kind of data sets and these kind of models, it is for sure that unboundedness creates this problem that can be solved by this linear increase. The problem in this particular case exists because of combination of the Adam optimizer and this effect that we have with the layer norm. So now that we understood that combination of things that happen there, and we want to control the parameters, how can we control those parameters? And the idea comes from another source. There is a paper called T-Fixup where they try to control the size of the change in the error by understanding how the parameters should be allocated or should be initialized. And they do a pretty good job in the case that you have a residual, just a feed-forward residual connection architecture with feed-forward blocks, with really simple MLP blocks. And they found a scaling that will work. So we did the math. It's like 5 pages of cute, really nice math. And we understood that we just needed to scale relatively to the number of layers and satisfying the equation that you see there. So as long as you're able to scale or you have your initializations to be in that order, you will be fine. And that led us to basically how we can remove the warmup, remove the layer norm, and what was the algorithm that we need to use. We initialize everything in the usual way, Sevier initialization and Gaussian initialization for different pieces. Then we scale the embedding according to the number of layers. For the decoder, we go with 9 times number of layers to the -1/4, and for the encoder, we go with 0.67. All this, the 0.67 actually has a lot to do with this math, and in order to make sure that the memory size is similar to the size given by the output embeddings. So that's the algorithm, and now we can actually look at the results. The first thing that we notice is that we got a new state of the art for machine translation. Like we got, like for every single data set that we try, like either a low resource data set like Romanian or a big data sets like WMT, we were able to beat every single benchmark that existed. And sometimes by a huge margin. Like anything that is larger than 0.5 for machine translation is a big gain. And more than that, we were able to beat, like, there are 2 kinds of baselines. The baselines that exist on the papers that are great, but if you go to the state-of-the-art implementations, like for example, the Facebook library called FirstSig has a state-of-the-art implementations that have a much higher baseline, and we were able to beat all those. So we were really happy with these results. But we wanted, like, there was something else that we learned. Like, in general, when you try to train transformers, before that, and we also noticed that our approach, like, solved the problem of the gradient vanishing in the embedding layers. So it was great. Like, it had all the features that we wanted. But the other thing that happened is, like, if you try to train transformers or BERT-like models, you find out that it gets hard if you try to go deeper. Like, going deeper is extremely difficult, and it has to do with this signal and these layer norms. And people have tried to do that before with some degree of success, but nobody has been able to train something larger than 20 or 30 layers. In our case, we found that we could train with any number of layers, and we will actually reach much better performance than any other approach. Furthermore, with a model with less number of layers, a smaller dimension, we are able to do much better. This is something they call the base model. Our base model does, if we go deeper, does much better than if we train with a big model, that state-of-the-art big models. So we're able to reduce the number of parameters by about 40% and get leading accuracy, leading blue score for our model. And that was pretty exciting. So we tried to actually go deeper. What is the deepest we can go? So we have some technology constraints in the sense that, I mean, we have good resources, but like, we don't have the resources to train like 200 layers with a high dimension model. So we train a really small model with a 128 64 embedding dimension, but we went to 200 layers. This corresponds to more than 1,000 different layers between self-attention, encoder attention, and feed-forward layers. And the models train. And not only they train, like, you can actually see gaining as you go deeper. We didn't do hyperparameter optimization. We highly suspect that we increase the dropout in these models, we will actually do better. But we didn't go that way. We were just happy that you can go deeper, because this opens a whole new area of research. And techniques like layer drop may actually be able to improve the capacity of these models by giving the proper kind of regularization that they need. So going back to what I was telling you, hub-field networks, if you increase the embedding dimension, you are definitely giving capacity to your model, but you're suffering more for the course of dimensionality. But if you go deeper and lower the dimension, you're increasing the capacity of the model, but you don't have that problem anymore. So the model becomes relatively easier to optimize and to deal with. So those were our results for the ultra deep transformer. We also look at what happens if you train with different batch sizes, and compared to the transformer, our model is much more stable when training with different batch sizes, which is also surprising because the transformer doesn't allow you to do that. You need to be careful with batch sizes in the transformer-like models. And I think that's it. Thank you so much for listening. Thanks for being there. If you have any questions about this topic or about layer 6, we are hiring all the time. So feel free to contact me either through my email or send me a connection request on LinkedIn.
Philip has asked, how do BLEU scores work?
That's an excellent question, actually. So Blue score is how you measure the quality of a translation. The way that it works, doing automatic scoring of translation is extremely hard. So the way that they do it is like they check how many engrams or how many pieces match with a good translation. They just do a kind of an averaging, and that's how you obtain the blue. Like how many 1 grams I am getting, how many 2 grams am I getting, how many 3 grams I'm getting, and they do some weighting of that and some penalties because there are ways of cheating the score. But in general, the idea is the blue score is just a measure of the quality of translation. That's the short sense.
Thank you. We have a question from Jeremy. He wants to know your name, so it's Felipe
my name
Perez.
Is Felipe Perez, yeah.
Ganesh asks, what are your thoughts on attention-free transformers? Is it applicable to machine translation?
I'm not familiar with attention-free transformers, unfortunately. I'm assuming, like, if you remove the attention blocks if you remove the attention blocks from the transformer architecture, you just obtain a ResNet-like architecture, which won't have the same capacity. Attention blocks, in general, improve the capacity of the model significantly, and that's what this paper, the hub-field networks, is all you need is able to show. That paper is amazing because they show that the number of patterns that you can memorize with the attention grows exponentially in the embedding dimension.
Nice one. Yeah, it's certainly take a look at that white paper there. Julian has asked, do you think this performance increases will transfer to other NLP tasks such as question answering, summarization, text generation?
I strongly suspect so. So here is the thing. Like right now, we are trying to train BERT-like models using the same idea for this kind of task. In our preliminary results, we are seeing improve in really small models. The problem is that training big models is extremely expensive. Training a BERT model is really, really expensive. So we need to make sure that we have enough small experiments before we go to the large experiment. We are seeing some progress. So we suspect that those gains that we have found for the transformer will also apply for BERT-like models, and therefore they will transfer to Q&A and summarization and this kind of downstream task.
Thanks for that. Another one from Ganesh. Do you take word piece as input like BERT? What is the length of input embeddings?
So we take the same tokenization that PERSIC uses that is based on GPT-2. So like that's for the workpiece kind of setup. And the length of the input embedding, it depends on the model. Some models will have, I think, 512 and some others will have 2048. So it depends, like the base model will have 512 and the big models will have like either 1024 or 2048, I don't remember.
Thank you. Question from Philip. Philip has said, if you take an expert human translator and compute the BLUE scores for that human translator, how does that compare with state-of-the-art DL approaches?
That's a beautiful question. It is a beautiful question because this is an open area research. There are many, many kinds of measurements of translation, and none of them is good. There is Roche, there is one that is called BEER, that is the one that has shown to be closer to human translation. BLUE, there is a strong movement within the NLP translation community that aims to actually get rid of the BLUE score as the thing that should be used. The problem is the literature, all the literature, and the things that you are comparing against are always in BLUE. So that's what is used. But there is studies that show that BLUE is not the best thing in order to compare against human translation, unfortunately.
Awesome. Jeremy has said, thank you for your presentation. He says he has a question more about NMT. How strongly does this technique depend on data sets? As in, would it work to improve models where data sets are limited, i.e. for dialects with limited data sets?
That's actually a pretty good question as well. And that was one thing we were really excited about. Our model was able to do, like in these data sets where you don't have a lot of things, it's called low resources data sets. And we were able to do, like our gain compared against other models was actually much bigger in this low resources data set than it was in the large data sets. So basically a model like the usual transformer with our initialization or with our modifications, it has too much capacity and it doesn't regularize well enough. So you need more data, and with more data, it does better. It does like much better than if it has less data. Instead, our model does much better if you have less data or more data, but like the difference is much larger if you have less data. So yeah, it is good for this kind of data sets.
We got a question from Yang. He said, coming way outside NLP related fields, just wondering, is Warmup phase unique to transformer architecture training due to layer norm, or has it shown to be beneficial for other architecture outside NLP fields? That's
a really good question as well. So this Warmup phase seems to work seems to fix the problem with the AND optimizer. So most models that exist can train well with an optimizer. It has only actually I only know of two where I only know of one where you cannot use an optimizer, and I think it's because they didn't try this Warmup, like learning rate Warmup, like starting linearly, and it was in a variational model. So like the models in our second talk, like really similar to those models, if you try the add-on optimizer, it doesn't seem to work well, and I suspect it's because the same effect that is happening with this language, but besides, and I suspect in that kind of setup, like this linear learning rate will help. So yeah, that's as much as I can say there.
Great. And we have a question from Ganesh. He says, does this model work well for all families of languages? Does the model consider structural variation among languages?
That's a really good question. So like most languages that we train in are like, I forgot the name. So there are two kinds of language. There are several distinctions in languages. One of them is these languages that have these words kind of set up, like English, French, German, all that kind of stuff. And languages more like Japanese, Chinese, where you have like the characters. So like for those kind of languages, we didn't test. I suspect the performance will actually drop because those languages are much harder to deal with, but we didn't try. And in terms of word order, it doesn't really matter. Like those structural variations in languages, the self-attention blocks and encoder attention blocks are really good at dealing with those structural variations. It's only when it has to do with the amount of words in the language in which the tokenization will work really well. Like the GPT, the sentence piece, that kind of setup tokenization works really well for these like Romanian kind of languages. For Chinese, I don't like it gets the problem gets time and lot. It gets super hard. It gets super hard.